This is the first of several videos on the mole. The mole is 6.022 times 10 to the 23rd of anything. It is an important number, and it's called Avogadro's number. This number is sort of as important to chemists as 3.14 pi is to mathematicians. Now, why is this an important number? Well, because it's just useful in terms of this unit called the mole, which quantifies matter. So the best way I can show this is by giving you an example so you kind of understand it. So let's say we're dealing with oxygen, right? Now, oxygen has a formula mass of 32.00 AMUs, and that's average mass of an oxygen molecule because, we talked about isotopes the other day. One other little fun fact we're going to need to have in the background is the relationship between this unit called AMUs and grams. An AMU is a very small unit, like one proton equals the mass of about one neutron, which equals about one atomic mass unit. Sometimes they'll even just call it 1 unit. I've seen that on the regents for some reason, so just be aware of it. They're the same thing. They're used interchangeably. Well, one of these AMUs, is so small that its mass in grams is 1.66 times 10 to the negative 24th grams. And if you can't, understand what that number means, it means it's a point followed by 23 zeros. Then you get the 166. That's a really small fraction of a 1, right? So, and that makes sense because protons are very small. They don't weigh a lot. All right. Now, supposing I wanted to know what a mole of oxygen weighed. Well, I'd say that I have 6.022 times 10 to the 23rd O2 molecules. That's literally what a mole of oxygen is. It's that many molecules, a large number. So why did we pick this random big number? Watch how this works out. So how much would that weigh, you ask? All right, so let's find the weight of this. So we would have to, since one molecule, right, weighs 32.00 AMUs, notice I'm factor labeling this, but the molecules will cancel out, but the O2 won't, right? Nor will the AMU. We can do the math there. When we do this, I'm going to do it in my calculator. I'm going to pause for a second. So when you multiply that out, you get 192.7 times 10 to the 23rd AMUs, okay? Or, obviously I can put that in scientific notation as well. But that, I'm going to just hold on to that. I'm not going to finish the problem yet because the reality is I don't have an AMU measure in the back of the room. What I do have is a balance, and the balance is measured in grams. So what I'm going to do is convert that answer into grams. And I'm going to do that in one step. Instead of writing out equals and my answer and then doing a second step, I'm just going to do a second step in a factor label problem in which I'm going to convert, so I put my parentheses back, going to convert the AMUs, into grams. Now, 1 AMU is 1.66 times 10 to the minus 24th gram. So the AMUs will cancel and we'll get the mass of a mole of molecules in grams. Now when we do this, we find we get 32.00 grams. Now the reason why is because when you multiply this number times Avogadro's number, it multiplies out to 1. And so essentially you have 1 times 32 equals 32. The only difference, though, is now you have grams. So when I say I've got 32 grams of oxygen, I don't have 1 molecule of oxygen. And this is where you have to understand the concept. I have 6 times 10 to the 23rd molecules of oxygen. Now, I could do the same thing for something else. Like I'd do it for, let's say, helium, right? If I had 6.022 times 10 to the 23rd helium molecules, helium being a monoatomic, right? And each helium molecule, I won't make you look it up, right? One molecule of helium weighs 4.00 AMUs, right? The molecules will cancel out. But when I multiply that times 1.66 times 10 to the minus 24 grams over 1 AMU, my answer ends up being 4.00 grams. So here's the bottom line. A mole of something can be figured out just by looking at the periodic table. Once you get the formula mass, if you change the AMUs and put a G at the end of it instead, that number that you're getting is known as the molar mass. It's also known as the gram formula mass. And what that number is, it's the mass of a single mole of the substance, which means not one molecule, but 6 times 10 to the 23rd molecules. And it doesn't matter what you're working with. I could just do like a quick erase job here and turn this into H2. And if I did that, since this number would change from 4 to being 2, then this would change from 4 to being 2. And that's the mass of a mole of hydrogen. So basically, the formula mass expressed in grams is how much this many molecules of something is going to weigh. And that's essentially what the mole is. But if the formula mass is greater, the mass of a mole will be greater. And it's proportional, right? If one molecule weighs twice as much as another molecule, like, if I have 1 mole of hydrogen, it's going to weigh 2 grams. 1 mole of helium weighs 4 grams. Just make sure you understand, if I have 4 moles of hydrogen, right, or 2 moles of hydrogen, it will weigh twice as much or 4 times as much. It's all proportional. So to quickly summarize the mole is 6 times 10 to the 23rd of anything. A mole is a large number, but the mass of a mole can be easily determined. If you just look up the elements on the periodic table, so if you look up, let's say, H2O on the periodic table, you can look up, now I'm not going to bother with sig figs here. Each hydrogen weighs 1, so this would be like 2 plus 16. A mole of water would be equal to 18 grams. A single molecule would weigh 18 AMUs. And that's basically how you figure out how much a mole of something weighs.